Hi guys, today we're going to cover section 3.3 and we're going to talk more about functions, the symmetry, and the piecewise defined functions. So if you're looking at the notes, we talk about how to determine even and odd functions algebraically and geographically. Sorry, not geographically, graphically. And also the increasing, decreasing constant of the function and local min and max. Piecewise function, and the greatest integer function. So let's go ahead and get started. By the way, before we will be using the even and the odd function definitions and combine with symmetry to show if a graph of a function is even or odd. Okay. All right, so if you look at the first question on number 2 is that part of the graph of an even function is shown. Complete a graph using symmetry. Now, if you look at the definition for even, right? Even function means this. So the way I interpret this is if I make the x values opposite, then I still get the same y value or f of x back. So essentially what's saying is if you take a point on the graph, you make the x the opposite, the y value is still the same. Okay, if that is true, then the function is even. So what we could do here is this. This is 0, 2. And notice 0, 2, if you make the x opposite, right, 0 is neutral, so you can't really make it opposite anyways. So 0, 2 will stay. This right here is negative 1 and 4. So if you take the x value and make it opposite, negative 1 becomes 1. And the y value is still the same. This point right here is negative 2 and 4. So if you make the x opposite, that means negative 2 becomes a positive 2. And the y value is still the same. And look here. This is negative 3 and 0. So if you make the negative 3 opposite, it becomes a positive 3, and 0 is still 0. So our graph will look something like this. Right? We make the sign x value opposite, but we still get the original y value back. Okay, so that's what this definition really means when we apply this to the graph. Okay? Now, the part B, this time we're given a graph, but this is an odd function instead of even. So let's look at the definition for an odd function. Odd function is f of negative x equal negative of f of x. Okay, so notice again, same idea. If I make the x value opposite, then, but this time check this out. This time we have a minus sign with a negative sign in front of the negative x. So that means so it's not just the x value is opposite, the y value is also opposite. Okay, so the x and y value, they both had to change. Okay, so if you think about it, if we said earlier, if the x value, right, if x goes to negative x and f of x stays the same, this is a symmetry over y-axis. Right, because the x are opposite, so you switch sides, and the y value is the same. So you essentially flip it over the y-axis. Now, what happens when y becomes the opposite of y? So which means any y value, what you're doing, you're switching signs. This right here is symmetry over x-axis. Okay? So based on what we have here, notice both x and y had to change, right, to negative x and negative y. Or I should use a better notation. So that means for this graph to be odd, you have to have both. You have to have flip it over the x-axis and flip over the y-axis. So which means both x and y has to be opposite signs. So for example, this is 1, 1, right? Both x value and the y value has to be opposite. So the point matching 1, 1 will be negative 1, negative 1. The point 2, 1 here from the original, right? They both had to be negative. So this is negative 2, negative 1. This point right here is 3, 4. So that means flip it over horizontally and vertically, right? It has to be negative 3, negative 4. And the last point, 4, 0. Right? Both x and y has to be opposite signs. So this becomes a negative 4, 0. And if we connect the dot, this graph right here is our odd function. Okay. So yeah, so definitely these two definitions. Okay, these are the definitions that you have to use to show, right, to complete a graph of an even or odd function. Okay, either you have that one for the odd function or this one right here for even. Okay. All right, let's move on to the next problem. All right, next problem, we got to figure out if the following function is even, odd, or neither. So that means we need to take the definition that we just used, and now this time apply algebraically. Okay. So remind ourselves, even means f of negative x equal f of x. Odd means f of negative x equal negative of f of x. Okay, so first thing first, I am going to, for number part A, f of x equal 1/3 x to the 4th minus 5x squared plus 1. I am going to test for even first. Okay, so let's go and test even. So which means I need to replace the x with a negative x. So if you do that, that means all the x's becomes a negative x. Now check this out. Negative x to the 4th power, remember, the negative sign, when you raise it to an even power, the negative sign essentially disappears. So this is the same as 1/3 x to the 4th. And same idea for negative x squared, right? Negative raised to the even power becomes a positive. The negative disappears. So this is the same as 5x squared plus 1. Okay. And this right here is the same as the original. Oops. So this is even. Okay, a function cannot be even or odd at the same time. So if you found the function is even, that's when we can stop. Okay. All right. Part B. G of x equal 1 over x minus x. So plugging g of negative x, right? Both even and odd start out with negative x. So plugging negative x, you get 1 over negative x minus negative x. So this is the same as negative 1 over x plus x. Now, this right here is definitely not even because they're not the same. So this is not even. Okay, so now let's check to see if it's odd. Okay, so what we're going to do is I am going to keep going, right? And notice the odd function has a negative in front of the function, right? So that implies we need to figure out, can we factor out negative 1? And what happens? If we factor out negative 1, what I end up getting is we get negative parentheses 1 over x minus x. And in this case, if you look at it, what is 1 over x minus x? Right, 1 over x minus x, that is our original problem. So this is the same as equal negative f of x, or g of x, sorry. This right here is odd. Notice I'm able to factor out negative 1 in the front. Okay, and the stuff inside the parentheses is our original function. With that, you can tell this is odd. Okay, let's go ahead and move on to part C. Part C is h of x is x cubed minus x squared. So again, testing for even or odd. So plug in the negative x. Hopefully we get good results. Okay, negative x cubed is going to turn out to be a negative x cubed minus negative x quantity squared is going to be a regular x squared because the negative just cancels. And check this out. This is not same as original. So which means this is not even. Okay. Now, not even doesn't mean that it has to be odd. Okay, keep that in mind. All right, so now let's check for odd. All right, so remember, checking for odd means I need to be able to factor out a negative, right? Factor out negative 1. So if I factor out negative 1, what I end up getting is x cubed plus x squared. And unfortunately, this right here is also not same as original. So that means in this case, we have neither. Okay. So this function right here is not symmetric to the y-axis, nor it is symmetric to the origin. Okay, so not symmetric to y-axis, not symmetric by origin. Well, not by 2. Sorry, I mean 2. Not symmetric to origin. Okay. Okay, this one is a neither. Okay, next one. X to the fifth minus 5x, and this is k of x. So k of negative x is going to equal to negative x to the fifth power minus 5 times negative x. So this is going to be a negative x to the fifth plus 5x. This right here is definitely not even because of the original. Now factor out negative 1. We get negative x to the fifth minus 5x. Now this time, this right here is the same as original. So this is negative k of x right here. Right, x to the fifth minus 5x is the same as original. So this is the same as negative k of x, and this is even. Okay. Just a few different varieties of stuff. M of x equals 6. M of x equal 6 cube root of x minus x. So if you do m of negative x, you get 6 cube root of negative x minus a negative x. Cube root of side work. Cube root of negative x is the same as cube root of negative 1 times cube root of x. And cube root of negative 1 is the same as 1. Oops, sorry. So bring this back. So this is that's a negative 1 times 6 cube root of x plus x. So this is negative 6 cube root of x plus x. And this is definitely not even. Okay, it is not the same as the original. But again, check out by factoring out negative. When you factor out negative, you get 6 cube root of x minus x. And this right here, it's the same as original. So therefore, this function is odd. Okay. Oh, looks like I needed one extra page. Let me try this again. There you go. Alright, last problem for section 3. T of x equal x square root of x squared minus 6. So t of negative x is negative x square root of negative x quantity squared minus 6. Simplify this, you get negative x square root of negative x quantity squared is x squared. Okay. Now this is definitely not even because of that negative sign. But if you realize the negative x square root of x squared minus 6, this whole thing right here is that. So this is the same as negative f of x. Okay. So yeah, so this is how you figure out how this whether the function is even or odd algebraically by plugging the negative x and work your way out to see what kind of result you get. Okay. All right, let's keep going. Sorry, I know the video has a lot of pauses in this one because I had to kind of fend my kids off so they don't make weird noises while I'm recording. Yes, the joy of having kids running around at home while recording stuff. All right, next problem. Let's move on. Next problem is the state of open interval where each function, I can't spell today, each function is increasing or decreasing. And identify the. Looks like some of my words are cut off. Okay, but we'll make it work. All right. So if you look at the graph that we have here, I'm going to pull the graph up so just we can use it. This is that. This is right here. Okay. There we go. So when we're looking at which intervals are increasing and decreasing, so what we do is we got to figure out what does that even mean. Okay? Think about increasing, decreasing. Increasing, decreasing, what we're going to do is we're going to use slope. But you're probably going to be like, well, how am I going to use slope when this is a quadratic? Okay, what we're going to do is we're going to use the slope of a straight line. So we are going to take a line, right? Think about a pencil in your hand. We're going to put it right on the graph. So for example, here is my pencil when I put it right on the graph. Notice it is pointing down. Okay, so if you treat this pencil like a line, the slope of this pencil is negative. So that means this part of the graph is decreasing because the slope is negative. Okay, now if I take, so which means if you think about it, over here, if my pencil, right, is pointing up, so that means the slope of my pencil is positive. So this means this section is increasing. All right. So now let's talk about constant. I know I didn't say anything about constant, but constant means what? Well, constant is when the slope is 0. Okay, so take a guess where slope equal to 0 is. I'll give you 5 seconds. 1, 2, 3, 4, 5. That's really quick, 5 seconds. The slope is equal to 0 happens right at the vertex. Okay, if you're really taking your pencil and move your pencil on the graph, right along the graph, you're gonna see that as you're looping around the vertex, there will be an instant where your pencil is horizontal. Okay, there will be an instant where your pencil is horizontal. Right at that instant, that is when the function is constant. It is neither increasing nor decreasing. Okay, constant happens at the tip or the vertex. Okay, all right. So that means we just got to figure out what the vertex is. If you look at the vertex happens at 3. Now these go by 2s, so 3 and -1, right? So that means the function is increasing from the interval of 2, infinity, decreasing from -infinity to 2, parentheses, at constant at x equals 2. Excuse me. I don't know why I said 2. I misread. I meant 3. These are supposed to be 3s. Okay. And when they're asking for increasing or decreasing, they're looking for domain. Okay, they're looking for the domain. They don't care about the y values, right? When they're asking for when is the graph increasing, decreasing, they are looking for domain. All right. Okay. Well, we'll try a couple more of these. Okay. All right. This time, slightly different graph. Same idea. Function increasing or decreasing. So I'm gonna basically draw myself my little pencil. So I'm going up and then going down, going back up again. Okay, and notice where the turnaround part. This graph turns around at 2, 0 and at this value right here. Okay, I knew that we're not going to be able to tell that value exactly, so that's why I provided for you. Right, you just need to know how to use it. Okay, so increasing, again, everything is coming from left. So the function is increasing from negative infinity to 2, parentheses, and it is also increasing at starting from 4.667 to positive infinity. The function is decreasing between 2 and 4.667. And the function is constant, so it's neither increasing or decreasing at x equal 2, x equal 4.667. Okay. Remember, which one's going up, down, and up? It's almost like a roller coaster. Okay, almost like a roller coaster. All right, it's almost like a roller coaster. Okay. All right, now the other thing I want to add in is something called the local min and local max. Local minimum versus local maximum. Okay. There's the local minimum and local maximum is kind of like a secondary to global minimum and global max. Okay. Global min and global max means the absolute highest value and the absolute lowest value. Okay. Now, with our graph, right, this graph, if you look at it, it goes all the way up to positive infinity and all the way down to negative infinity. So in this case, we don't have a global min or global max. Okay. On the last problem, when we have a parabola opening down like this, right, this place we have a global min because we do have an absolutely lowest spot, but not in this graph. Okay, so therefore, we can only talk about local minimum and local maximum. Okay, local, it just basically means it's a regional max. Okay, so if you think about it, around this area right here, right, this right here, this 2, 0 will be the local max because that's the highest point around that area. Okay, then that means this right here, this section right here, the 4.667 and this negative 9.481, this will be a local minimum. Again, it's a regional min and regional max. It's not global min or global max. Okay? All right, so we'll look at one more. Now this graph here is a W shape, right? So let's point out our local min and local max first. Our local min would be these 2 points. And this peak right here will be the local max. Okay. Now, the local mean here, right? They're also the global. Right? They're also the global min because in this case, they happen to be the lowest value. Right? Out of the entire function. So, a local minimum and global minimum, they could be the same points, but the local minimum is not always the global minimum. Okay? Same thing for max. A local max could be the same as a global max, but it is not necessarily a global max. Okay, like in this case, we don't have a global max because the line keeps going. All right, here we go. So now, let's look at our increasing, decreasing. If it helps, again, draw yourself a pencil. Pointing down. Pointing up. Pointing down again. Pointing up again. So in this case, my increasing would be from negative 1.5A1, comma, 0, union 1.5A1 to positive infinity. Decreasing, when the pencil is pointing down, will be from negative infinity to negative 1.5A1, union 0 to 1.5A1. The constants that happens at my x equal negative 1.5A1, x equal 0, and x equal 1.5A1. Essentially, those are your local min and local max. Okay. So yeah, local min, local max is not. It's a fairly straightforward concept to talk about, but we just gotta kind of make sure, make sure we don't get them confused. The increasing, decreasing. Again, for me, I like to use a pencil because my pencil is like my straight line. So I'm going to think about the slope of my pencil, and that helped me tell, as I go from left to right, which section of the graph is increasing or decreasing. Okay? All right, let's move on to the next one. The next one, we're supposed to graph and evaluate each piecewise function. So let me pull out the graph and see what we have. Okay. All right. So here we go. Our function, I'm going to write in the upper corner. This is f of x equal negative 3 and 2x plus 3. And negative 3 happens when x is less than 0. 2x plus 3 happens when x is greater than 0. Okay, and we're supposed to figure out what f of negative 2 is, f of 1 is, and f of 0. Okay, so before we graph, let's figure out these individual values first. Okay, so when you have a piecewise function, this right here, the x less than 0, greater than 0, this right here, that's your domain. Okay, so that means these graphs, negative 3, 2x plus 3, will only happen if the x is in the domain. So let's just go ahead and figure out what f of negative 2 is. If you're trying to figure out f of negative 2, right, that means I got to figure out when x is less than 0. So f of negative 2, I have to use this one right here, because this first equation happens when x is less than 0. So f of negative 2, the answer will be negative 3. Okay. Same idea for 1. F of 1. 1 is greater than 0. So for f of 1, I have to use this right here, where x is greater than 0. So f of 1 is 2 times 1 plus 3, which is 5. Okay. Now check out the last problem, f of 0. Notice, is 0 in any of them? Is 0 less than 0? Is 0 greater than 0? Both of these are no. So which means in this case, f of 0 is undefined. Okay, f of 0 is undefined because it doesn't work in any of the domains. None of the domains takes 0. Okay? Alright, so let's go ahead and graph this. The graphing is going to be a little bit weird because you're going to be like, well, what do you mean? What do you mean? What do I do at the endpoints? Okay, when you're graphing, focus on the endpoints. Okay, so for example, if you look at the first equation, right? The first equation, you have negative 3. So that means it is negative 3, so negative 1, 2, 3, until I hit 0 for x. So that means over there, I need to put a open circle. Right? And for the second equation, 2x plus 3, right? I'm just going to pretend I'm going to graph 2x plus 3, but I need to figure out what happens at x equals 0. Right? So if I plug in 0, I get 2 times 0 plus 3, which is 3. Okay, but didn't we say earlier that this is undefined? So that means at that point, I'm going to put a circle right at 0, 3. To show that at 0, 3, it is undefined. But I'm going to graph the rest. So, if you know how to graph, right? We start at 3 and goes, the ratio is up to 1 to the right. So up to 1 to the right, up to 1 to the right. So this is what our graph looks like. This is a piecewise function that they're not connected, and they just each take on its own depending on the domain. Okay, the y equal negative 3 or f of x equal negative 3 is a horizontal line that only happens when the x value is less than 0. And 2x plus 3 is a linear function that only happens when x is positive. And at x equal to 0, they're both, notice they're both open circles, therefore it is undefined. Okay? It's a little weird. Alright. The next problem, unfortunately, it's going to be I decided to throw you guys a curveball. Okay? It's going to be a little difficult. And I'm pretty sure we can do it still. So you got negative x minus 2, absolute value of x minus 2, and you have x plus 2. And these happens when x is less than negative 2, x is between negative 2 and positive 2, and x is greater than 2. Okay? And we're still going to find f of negative 2, f of z1, f of 4. Okay. So first problem, f of negative 2, right? Let's look for the domain. Which equation will accommodate x equal negative 2? It looks like x equal negative 2 will be accommodated by the equation in the middle, right? Notice x is between negative 2 and 2, but inclusive of negative 2 and 2. So which means f of negative 2 is going to be the absolute value of negative 2 minus 2, which is absolute value of negative 4, which is 4. Okay. F of 1, right? So we got to figure out which equation will handle 1. Well, it looks like 1 is the same as again using the second equation, right? Because 1 is between 2 and negative 2. So again, this is going to be 1 minus 2, which is negative 1, which is 1. Okay. Third problem, f of 4. 4 is bigger than 2, so 4 will have to be in this one. So we have to use the equation x plus 2. So f of 4 is 4 plus 2, which is equal to 6. Okay. So graphing this, now we have 3 separate equations that we have to graph. So this might look a little goofy, right? But let's think about how we graph this. So first thing first, what I'm going to do is I am going to graph negative x minus 2, pretending that there is no limit, no restriction on the domain. So negative x minus 2 tells me that I need to start at negative 2, and then based on my slope is negative 1. That means I gotta go down 1 to the right. Okay, so that means I can keep going. I can do down 1 to the right, down 1 to the right, down 1 to the right, or I can go up 1 to the left, up 1 to the left, up 1 to the left. So if I connect the dots, this is what I have. Okay, just graphing like normal. All right. Now, the issue here is once we graph it like normal, right, because our domain is restricted, I am going to erase the sections of it that is not in the domain. So that means anything that is greater than or equal to negative 2 has to be erased. Any x value, any points with an x value that is greater than or equal to negative 2 has to be erased. So that means all this is gone except for this right here. Only this section remains. Okay. All right. Now, the first section is done. Now, let's work on the second section, the absolute value one. Remember, absolute value is a V shape. Right? It's a V shape. Typically has a vertex at 0, 0. But the x minus 2, right? Remember, which direction is it going to go? X minus 2 is going to make it go to the right. So this means I have a V shape starting at a 2, 0 and then goes like that. Sorry, I can't draw straight lines. Okay. Now, check this out. This absolute value only happens between negative 2 and 2. So that means anything greater than 2 or less than negative 2 has to be erased. So that means this equation actually only looks like that. And it is a solid dot because it's less than or equal to. So okay. So this equation actually, even though it's an absolute value, because of the restriction, looks like it's just a straight line. Okay. All right, x plus 2 is, so we're done with this absolute value. Now the last equation, x plus 2, happens when x is greater than 2. So again, I'm just going to go ahead and graph the line. I'm going to use a different color this time because we're going to cross some stuff. X plus 2 means I started at 0, 2, then I go 1 up, 1 to the right, and keep going, and going, and going, and going. Okay. And once I draw my general line, I'm going to look at my domain. Domain says this green line only happens when x is greater than 2. So that means there's an open circle right at 2. Now I had to erase anything before that. And there we go. And this right here is the graph of this piecewise function. Okay, you're just gonna have to look at each piece individually, graph it, and then restrict it. All right. Okay. Oops. All right. So now the last part, the greatest integer function. The greatest integer function essentially to me is a round down function. Okay, so for example, if you have 1.57, right? We're going to round it down to the nearest integer. So that's going to be 1. Right? 1.99, that is still 1. 0.57, that's going to be 0. Okay. Negative 1.528, something like that. Right? We're going to round it down to negative 2. Notice we're rounding down, right? Negative 0.25, 25 cents, negative, right? That's going to be round down to negative 1. Okay. Now, what about integers already? If the number is already an integer, say for example 3, you don't get to round it down. 3 is just 3. All right, 2 is just 2. Negative 5 is just negative 5. Okay, we only round it down when you have a when it's a decimal, right? When it's a decimal in between, when it's a decimal or fraction, or technically any number that's in between integers. Okay, all right. So that's it for the greatest integer function. Again, any questions? Feel free to post a question in the forum. Blackboard. You can find me, send me an email, WHSIEH, or office hour. Office hour, remember, is 6 p.m. to 8 p.m. Or give me a call, 616-234-4729. Okay? All right. Good luck. We'll see you guys soon. Bye.